It doesn't matter. Anyways, I need the software installed. It's called Audacity. Can you help me?
Yeah, sure. Yeah. Just type in sudo apt install.
Okay.
Audacity. Yeah, now type in your password.
Tunnels are everywhere, most of the time we're unaware, but horses know we're leaking all the time. When looking in the fridge, when coughing just a bit in bridge, use tunnels for fun and for the prize, cause tunnels are with us all the time.
How do you even log into your system, Manuel?
Well, auto login.
Auto login?
Yeah, so you see, I really do need this software until next week Saturday, because some presentation, you know.
And?
Well, you know, last time the guys helped me recover the pin. I don't know what they exactly did, but in the end it kind of worked out.
Look, it's not that simple. The operating system just doesn't simply store the passwords in plain. They use something like a hash function.
Okay, and what's that supposed to be? Can you eat that?
No, so it's like an irreversible operation you apply on a plain text like a password.
What? How can operation be irreversible?
Yeah, how can? I mean, you think of it like an arithmetical operation. You add two numbers.
All right.
And you need to find out which two numbers you added together.
So, like if I take 3 and 3 and it's 6?
Yes, exactly. But you don't know if it's 3 and 3 or if it's 4 and 2 or 5 and 1.
Okay, that makes sense.
So it's like a trapdoor.
Okay, I see.
Huh. I never thought about it that way. Yeah.
Hey! Dude, can you help me? Recover my password, you know, I forgot it again.
If you forgot your password, how did you even install any updates on the system?
Updates?
Wait a second. 5,321 packets to update.
Is that bad?
Oh my god.
Wow. That's completely outdated.
Now, is that good or bad?
So actually it's good, because if it's outdated, we might find a way to exploit the system, run a kernel exploit on it.
Because it's a very old kernel.
Exactly.
Let's see which one is running there.
Do you have to reinstall it? So as in you help me or do it for me, because I can't do that.
Oh, okay guys, I got an exploit.
Okay.
But this one assumes that ASLR is turned off.
Turned off?
Yeah.
We actually, Jonas had an ASLR break last week, but that was on the hypervisor and an older machine than this one.
Again, ASLR?
Yeah, I mean, it's a different thing than last time, different attack. Last time it was branch prediction, which is closely related to Spectre. But today it will be Prefetch, which is closely related to Meltdown. The Prefetch instruction takes virtual addresses, but it fetches physical memory into the caches. So it has to translate the virtual address to a physical address.
Yeah?
There could be timing difference there.
Yeah, you're right.
Yeah. So the students usually implement it in a way where they abort the translation as soon as they reach an invalid bit. So,
do you think the hardware would do the same?
Well, if you think about it, what would they do? I mean, they can't really continue translating because the bit there is invalid. There is no next layer.
So, what happens if you prefetch an invalid address? Does it crash the program?
We can try that out. Look at this, my measurement code. It doesn't really work.
Did you fence it?
Yeah. Here, mfence, RETC, and then mfence again.
Let me check something. It's just a hint, right?
Oh, so that means it could be completely ignored.
Yeah, maybe.
But the timing is different when I perform no prefetch at all.
So here it says the prefetch instruction is not ordered with respect to the fence instructions.
Okay. But I thought that L fences and M fences make sure that everything before them is completely finished.
I think you probably need a serializing instruction.
Like which one?
CPU ID.
CPU ID.
Yes. If you use CPU ID with arguments as zeros, then it's fully serializing.
Oh. Huh. That's interesting. Well, let me add that.
Oh, that's interesting.
Hmm?
There's also some part about non-determinism.
Okay. Non-deterministic. Sounds like they didn't want to explain what is actually going on.
Yes.
So next I need to figure out the corner cases.
So what would be the corner cases here? Like cached and not cached?
Yeah, these two make sense for valid addresses, but for invalid addresses?
The mapping level.
Ah, yeah.
Actually have 4 levels.
4 levels of paging, yeah? If the translation is valid on the first maybe 1, 2, 3 layers, but then not on the remaining ones. Well, I'm really wondering whether that would be visible in the timing.
Might be. So let's try that out, but don't forget about the serializing instruction. Look at that.
Ah, yeah, the page translation tables. And the more levels you have, I mean, the slower it should get, right?
No, but it's faster.
Maybe there's some caching?
Ah, yeah. There's a TLB.
A TLB?
Yeah, a translation look-aside buffer. So translating virtual addresses to physical addresses, that's a lot of memory access that you would have to perform. With 4-level paging, for instance, you would have 1 memory access that you want to perform, but it wouldn't be just 1 memory access into the physical memory. You would actually perform
5 accesses, 1 for each layer.
But that would be slow, right?
Yeah, but that's why there is a TLB. When you look up some virtual to physical translation, then you will store the result of the virtual to physical address mapping in this cache, in this TLB.
And actually, there's even more today. So if we take a recent Intel or AMD CPU, and you have the first lookup in the L1 TLB for instructions and data, and then you have the unified L2 TLB.
So unified means for both code and data, right?
Yeah.
But additionally to the TLB, there's also further caches. The TLB could be seen as a cache for page table entries, kind of a PTE cache, right? But then it can also store translations for 2 megabyte pages very often. So it really stores virtual to physical mappings and the page size.
But what if it's not in the TLB?
Well, if it's not in TLB,
Well, what would you do?
we cannot go to DRAM, right? It would be too slow. So what's the solution? Let's add more caches.
And that's exactly what they do. So they have a next level cache, a PDE cache usually, and then a PDPTE cache, and then a PML4 cache.
Okay. But some CPUs, I'm not sure what you're reading there, but some CPUs actually don't have separate caches for PDE, PDPTE, and PML4. But they have a unified cache where some of those entries are stored together. Maybe even PDEs in the same.
And if all of them miss, then we need to go to the DRAM, right?
No.
You think there are more?
Well, these entries, they are just data, right? So they would end up in the normal cache hierarchy as well. So we can also add L1, L2, L3 to this drawing.
Right.
Oh, okay. So, but then we get it from DRAM, right?
Yeah, I think so.
Okay. I think I know how to break ASLR. We can just prefetch kernel addresses.
Doesn't that cause a seg fault?
No, it shouldn't. Prefetch should not fault on either kernel or user space addresses.
Ah, okay, but then that makes sense. Because if you iterate over some data structure in a loop, and you are in iteration n, you already want to prefetch the data for iteration n plus 1. But then at the end of the loop, n plus 1,
That's out of bounds, right?
it's out of bounds, yeah?
Hmm.
And then it would be bad if it faults.
That makes sense.
And you said you want to prefetch the kernel address?
Yeah, exactly. So guys, put this on.
Whoa,
Whoa.
you're all glitching.
Why are you wearing a tie? Let's say we go in 512 gigabyte steps over the entire memory. So we can see where a PML4 entry is present that covers a 512 gigabyte aligned memory block and where it is not.
Yeah.
The present bit has to be set if the kernel is mapped within this 512 gigabytes.
Or anything else.
Oh, you're right, or anything else.
Yeah.
What a pity.
Like code down there. I don't know what this is.
Is that a problem? We just find all the regions in the kernel that are mapped.
Yeah. And in the user space.
Right.
Wait, but the kernel code should be very far up there.
Maybe this one here?
Oh. Interesting, but there's rarely any peak downwards. This one, yes, at the very end of the kernel address range.
That could be the kernel, yes.
So this is not 512 gigabyte steps anymore, but this is now 1 gigabyte steps for the page directory pointer table entries then.
Exactly, and now you see that the small dip where the kernel code should be.
Right, so let's go through this in 2 megabyte steps.
For the page directory entries. Wow, you can really see that here in this range, there's kernel code there.
Oh yeah. So let's zoom into that again, now with 4 kilobyte steps for the page table entries.
Okay, let's do that. Oh, that looks all the same.
Oh.
All low timings, yeah. But according to the documentation, the kernel code should actually start here. But it doesn't. And instead, the timings in this area are pulled down to this 2 megabyte range. How can this be?
Ah, yeah. I think that could be kernel address space layout randomization.
Oh.
All right. Yeah, I can't open it right now, but I'm sure it sounds great. Guys, do you have time on Saturday 8 p.m.?
Saturday, 8 p.m. What's that?
I think Manuel's presentation.
Yeah, my side channel thing.
I guess I have time, yeah?
Cool. Yeah, you should all come and bring people as you like.
Anyway, Martin, that's the address you can provide to the exploit.
Oh, okay. One moment. So I'm running the Prefetch exploit to get the offset.
Okay.
Now I run my exploit with the offset. Let's see. Oh yeah, it worked.
All right.
That's great, yeah?
Very nice.
So-
Thanks, guys. Then looking forward to seeing you on Saturday. Don't forget.
Wait, was that the project that you've been working on?
We will never know.
I almost overlooked. We found a new side channel.
So, what do we call it?
The Prefetch side channel attack. Vulnerability names logos, I don't know, songs, trailers. That's important.
Yeah, but that's marketing. Real science shouldn't do that.
It's not just marketing, it's communication, right? If, let's say you have a vulnerability and you call it, let's give it a fancy name, let's call it shark attack. You will never be able to Google that.
Probably not.
Yeah, there's lots of stuff on shark attacks on the internet. But everyone knows the law of Pythagoras, because it has a great logo. For efficient communication, you don't want to name it by the CVE number, right? So you want to have a simple name that you can easily memorize and that you can use while talking about it. Otherwise, people will come up with their own names for it. And that's what is important here. And that's why it's important to emphasize that people should give their attacks and their research proper names that speak for themselves.
The prefetch side channel attack, you say? You should really check your name ideas before doing all the work.
Prefetch side channel attacks.
So there is another paper, it's concurrent work by Young et al. And they also scan memory, but they only get 2 different timing levels.
How does it work?
So they exploit a feature called TSX. TSX has 2 important features. It's called TSX begin and TSX end.
TSX?
Transactional synchronization extensions for transactional memory.
Oh, that sounds like database transactions.
Yeah, let me show you.
Okay.
If you need to do some atomic operation,
Yeah.
you would need to lock it, right? Either with a mutex or a spin lock. So most of the time, the lock is not held by anyone, right?
Yeah.
So you're basically wasting time.
That's true.
Transactions have this nice property that you begin the transaction, perform a bunch of operations, and or commit the transaction. And if there was no problem in the meantime, the transaction succeeds or it aborts.
Okay. But a problem, you say a problem. What would be a problem here?
Yeah, think of something like a concurrent write access.
If that's a problem, then how do you replace the mutex there?
That's a good point. So in the case there was this concurrent write access, you would need to replace it again with a lock.
Ah, so that's the else condition then.
Yes, you use the normal implementation then.
That's quite neat, yeah.
Yes, and it's pretty fast, right?
Because most of the time you don't need the lock. But how do you exploit that? You said you want to use that for an attack?
Exactly. So what happens now if you're trying to access something that causes a fault? For instance, a null pointer or a kernel address from user space.
What do you think happens?
Yeah, I think it has to abort. It does not succeed there, right?
Ah, and so you want to try now addresses in these TSX transactions, like in there.
If you probe all the kernel addresses with that, you can see which addresses are valid or not, because the TLB handles them faster or slower.
Ah, and it gives us 2 timing levels when measuring how long the TSX transaction takes. And based on that, we can find the start of the kernel modules or the kernel code or data again.
Exactly.
Nice. And it's exactly at the same place as with the prefetch attack. Very good.
Awesome.
All right, guys. See you on Saturday. Thanks again.
So, this one here.
This is the address that Manuel gave you?
Yeah.
That's not a university building.
It could be a university building.
It says club.
Also, did it occur to you that Saturday is a little bit of a weird time for a university course?
I didn't think of that.
Hey, look who showed up.
Manuel, this is not for a university course, is it?
Well, no. You see, our band, we had a challenge to write a song about our flatmates, but without asking or telling them.
Oh God. The card that we cloned for you,
Yeah, so I don't need a 2 class cut. I don't study there.
Wait, you're a student?
Well, yeah. I didn't tell you, but I'm studying.
Everywhere, most of the time we're unaware, but horses know we're leaking all the time. When looking in the fridge, when coffin does the bidding bridge, you sergeant owls for fun and for the prize, cause sergeant owls are with us all the time. In software it's the same, we automate a channel game, leakage within all it's optimized. Caches leak and DRAM leaks and branch prediction really leaks, so last resort is reading power spikes. Sergeant owls are with us all the time. And if you see some noise and ask its data, we still need to pass leak pin and password key and all the like. Transients, but even with a new defense, the sergeant owls are with us all the time. The sergeant owls are with us all the time. Yes, sergeant owls are with us all the time.